Now that we understand the joint mechanics, we can discuss in more detail the parameters that affect joint strength in Module 27. So now we know how to design a joint. We can use analytical models, we can use more sophisticated tools such as the finite element analysis, in particular cohesive zone elements. But let's go back and try to understand now which parameters affect the joint strength, the overlap especially, and what happens when you use mild steel or high strength steel or composite materials. Let's talk about the general trends. We have a better idea about the parameters that affect joint strength. And let's start with the adhesive thickness. The thinner is the bond line, the stronger is the joint. This is basically related to the bending moment and the peel stress. It's quite easy to understand. But of course, you shouldn't abuse and use a too thin bond line, because you will reach a point where the substrate will start to go into each other because there is not enough adhesive. But generally speaking, for structural adhesives, we are talking about 0.1, something like that, for the optimum adhesive thickness, such as indicated here. You have here the failure load versus the bond line. Now, for flexible and elastic adhesive, it might not be 0.1, because these adhesives can distribute better than load, can make use better of the adhesive that we put, and it might not be 0.1, it might be larger, thicker, the bond line. Okay, let's see now the overlap, and let's start where the case we have high strength steel. So the steel will not deform plastically, okay? The substrate will be in the elastic part. We have a graph which represents the failure load versus the overlap, and we have two cases here. We have a case where we have a brittle adhesive. Brittle adhesive, we are talking about an adhesive which is practically elastic to failure. In this case, the overlap practically has no effect, because when we have such a behavior for the adhesive and we look at the stress distribution along the overlap, everything takes place at the ends of the overlap. And it doesn't matter to use a short or a very long overlap, the middle is doing nothing. That's why you have a plateau for the failure load. Now, let's imagine we use a very ductile adhesive, okay? A lot of plasticity. Then the whole overlap will contribute, because there will be a stress redistribution, I remind you, and finally you have global yielding of the adhesive. So the whole overlap contributes. So you have proportionality between failure load and overlap. Let me show you again. I have shown previously this joint, but I show again. This is a typical case. You have a 2K polyurethane, two-part polyurethane, very ductile, and the whole overlap has yielded, okay? And you have perfect proportionality between the overlap and the overlap. That's the ideal situation. You really take advantage of the whole overlap. You can only do this if the adhesive is very, very, very ductile. If it's brittle, doesn't matter to use 50 or 25 or 12.5. It will be exactly the same result, okay? Okay, now let's look at the case where you have low strength steel or aluminum. Again, same graph, failure load versus overlap. Let's start with the case where the adhesive, or in all cases actually, the adhesive is ductile, okay, very ductile. But let's start with the case where the strength of the steel is quite high. You have a nearly proportionality. We are back to this case really. The adhesive can work in peace and it will yield nearly along the whole overlap. It's not very, very ductile. It has a limited ductility. We are talking about this case, not a very, very ductile adhesive, an adhesive with a limited ductility. It's not perfectly proportional. If it was very ductile, you would have proportionality. Now, let's look at other cases where you don't have high strength steel, but you have mild steel. What happens is that the steel will yield at the ends of the overlap and will be permanently deformed and will cause premature failure of the joint because it pulled locally the adhesive. The adhesive has a limited ductility and will eventually fail. You see, you have adhesive on both sides, but what controls failure is not the adhesive, but the yielding. You can see it's very clear how it permanently bends. It's the yielding of the steel that controls failure, okay? Again, in this case, what's the effect of the overlap? It doesn't matter if you use long or short, everything happens at the ends and corresponding to the yielding of the steel. You have a plateau corresponding to the yielding limit of the steel. If it's very low strength yield steel or mild steel, then the plateau is very low. As you increase the yielding stress of the steel, this plateau is increasing. Here you go from very mild steel to intermediate steel. And if you increase a bit further, you go here until you go to the case where you have high strength steel. And then it's the adhesive that controls failure and not anymore the yielding of the steel. Okay, now let's imagine we have composite. Again, ferroload versus overlap. And we start with a case where we have a relatively flexible adhesive, such as a toughened epoxy, for example, or two-part polyurethane adhesive. In this case, again, you have proportionality because you don't have delamination. I show you here, this is composite material, okay? And you have adhesive on both sides, very irregular, it plastically deformed, you load it and it failed in the adhesive, and the adhesive could give its full potential and made use of the whole overlap. You have proportionality. If you use a long overlap, because the adhesive is very ductile, it will make use of the whole overlap and you will have perfect proportionality, okay? That's exactly what you want. That's why in cars, for example, that use composite, they would use a relatively flexible adhesive such as a two-part polyurethane so that you don't have delamination and you can make use really of the whole overlap. Now imagine you have a stiff epoxy. This is what you have delamination. And in this case, doesn't matter to use 25 or 50 or 12.5, everything happens at the ends of the overlap due to the delamination of the composite. And you have a plateau here corresponding to the delamination of the composite. Okay? So you have different plateaus, but for different reasons. In this case, it's due to the fact that the adhesive is too brittle. Everything takes place at the ends of the overlap. In this case, it's the yielding of the steel or the aluminum. In this case, it's the delamination of the composite. So you have plateaus for different reasons. The ideal situation is to use a very ductile adhesive, not too stiff in the case of the composites. Here, in the case of high strength steel, a very ductile adhesive, and in the case of low strength steel, there is not really anything to do because the steel will control the failure. In the case of high strength steel, it's to use a very ductile adhesive to make use of the whole overlap. Okay. Just before finishing this module, let me talk about the effect of temperature. This is an important part. The temperature will cause a difference in thermal expansion between the substrates when you use different substrates. If you use the same substrates, it's not a big deal. But if you use, for example, aluminum and composite, you might have problems because they don't expand the same way. Imagine you heat them to high temperature and then you cool down. When you cool down, the metal will change and it will the dimension will be shorter. The composite, it doesn't change because the composite has a nearly zero coefficient of thermal expansion, and this will strain the adhesive. Just the change of temperature will strain the adhesive. And if you look at the shear stress, one part will be negative, the other part will be positive. And then you load, mechanical load, and the stress will be something like that. So if you add this plus this part will be very highly loaded. This part will be very lightly loaded. And this changes completely the stress distribution in the joint. So when you have temperature involved, the stress distribution that we previously discussed changed radically. So be careful when the temperature is involved and you use dissimilar substrates.